We begin this training film for the 3 Williams number 60 DF pulverizers with an overall view, starting at the local control panel where manual operation of the system is possible, and panning up to the wind box and the pulverizer while it is in operation at 92% load. This man has just climbed to the spinner separator level, where the coal is sized by spinning angle iron blades. This is an overview schematic of the Foster Wheeler boiler with the Williams pulverizers located at the ground floor, the burners located several stories higher, and the upper furnace section complete with superheater and convection section. We will now examine the electrical schematic for the pulverizers.
Drawing number 102D 9956, page 1 of 11.
I'm going to zoom up to you now. Okay, go ahead.
Coming in with 480 volt 3-phase power into our disconnect. Terminal blocks 1L1, 1L2, and 1L3. Then, in turn, go through 340 amp fuses, F1, 2, and 3, in the transformer T3, which is 15 kVA transformer feeding our spinner drive. We also take that 440 volt power and feed F4 and F5 in the transformer T4.
Where are those? Point to. No.
We have fuses F4 and F5.
Alright.
Feeding our 440 volts into T4 with a 0.5 kVA transformer with an internal transient surge suppressor. This is giving our control power for all our local panels and our discrete inputs and outputs.
Okay, would you please show me all that now?
Okay.
In the panels.
There's our incoming power through our disconnect. The terminal blocks are located L1, L2, and L3.
Okay.
Our fuses F1 through F5. First three feed power into our transformer or our classifier drive, 15 kVA transformer. And in turn fed back down into our spinner drive.
Where's the spinner drive?
Spinner drive is located right here. That is the Sabre 3300 DC drive, 3-phase drive.
Okay, hold a red drawing. Are located up there, and what do they feed?
They feed into transformer T4.
And is that what you're holding?
Yes.
Alright.
Which feed all our control power to our discrete inputs and outputs.
Okay.
Our discrete inputs and outputs are located on the side of the panel.
Point to them, please.
Inputs being the top 2 racks, outputs being the lower 2 racks.
Alright.
We also take power out of T4, feed T2. T2 is our computer transformer. All the control power to the computer and to the E-stops and the NCR through these 2 relays here.
Okay. F-mill schematic, drawing 102D 9956.
Right. Sheet 2 of 11.
Alright. Okay, go ahead, Mark.
Okay, first thing we have in our drawing is power supply 3, which is an auxiliary power supply for our G-to-A modules.
Okay, speak up.
We also go through F13, need an on and off switch into an EMI filter and a computer on-off indicator. Our EMI filter in turn feeds PS2, which is our computer power supply, plus 5 volts to 28 amps, plus and minus 12 volts to 3 amps. This power comes into our card cage, which houses our CPU module, our discrete I/O module, our E2PROM and signal conditioning board, our A to D conversion module, and D to A modules.
Okay, you want to show me those?
Okay. First of all, PS3 is located here.
Wait. PS3 is there.
Right.
Alright.
Show us F13. F13 is down here. That in turn feeds power to the CMI filter. Power goes from the EMI filter
Alright.
to the on and off switch
Alright.
into our power supply.
That's the power supply.
Our incoming power is located on the left side of the power supply.
Okay.
Plus 5 volts are your top two terminals. The next two terminals are plus 12 volts. The bottom two terminals are your minus 12 volts.
Okay.
Inside this enclosure we have to house our computer and all our signal conditioning.
Please point to them.
Our card cage for the computer. First board being our E2PROM board signal conditioning. Our A to D converter card. Our CPU card. Our discrete I/O card. And our D to A board.
Okay, this is 102D9956.
Page 3 of 11.
Alright, go ahead. What do you got on there?
Okay, this is our input module layout
Point to them.
and wiring for the
What does that read?
discrete inputs. First input number is input number 1, which is okay to start pulverizer system.
Okay, you don't have to go through all of them. This is just the variety of them.
Gives your layout of your inputs. We have 1 to 32 inputs.
Those are all inputs on that sheet?
These are all inputs.
Okay, show me where the inputs are there. In the cabinet.
Inputs are located on the top rack inside. And the first input is pulverizer start.
Alright.
Second input is okay to turn on and engage eddy current
Are
clutch.
those in the same order as they're shown on that sheet?
Correct.
Okay, and you'll see that they're all labeled here.
Saying exactly what they are and what they do.
How many inputs do you have?
Okay, we have 14 inputs.
And the upper two then are
spares.
Are spares.
Everything.
And you have an extra 16 spares.
Correct.
All right, thank you. The lights at this time so that we can show the LEDs. Go ahead, would you please show them?
These LEDs show the status of the input. Some of these inputs when they're engaged or off.
Point to one that's on, please.
Okay. First one that is on is spinner over temp. That means we have a normally closed switch coming into this input. If this light would be off, that would mean that we have an over temp indication, which would be firing an alarm on the CRT in the main control room.
What's the one above it?
And the one above it is the ECC cooling system pressure switch, which is a normally closed switch. When we have pressure, this switch opens. If not, we fire an alarm and shut down the entire system. You would not have any water flow to your clutch.
Sheet and 102D9956.
Page 5 of 11.
Okay, we skipped one sheet, is that correct?
Correct. That sheet showed the rest of our inputs.
Alright, that was the following inputs. Alright, now, what do we got here?
Okay. This sheet shows some of our outputs. These are our output modules for the computer. Okay. Coming out of the output module on some of the outputs, we have indicators and or relays, which fire the according output to a motor starter and indicate with an indicator on the local panel.
All of these then are your outputs. Would you please point to your outputs?
Our outputs are two lower racks, which are black. Our outputs start with number 1 being on the bottom inside rack. Those go from 0 to 16, or 0 to 15, and then 16 through 31 is on the second rack.
Okay.
All of these outputs are fused. A little 5 amp fuse, which is located above each output module.
Alright.
The statuses can also be shown on the LEDs.
Okay, I got to turn.
Shown lit. When I have my finger on, shows pulverizer shut down complete, which is a status to Forney, saying that we have shut down completely from a prior startup.
Okay.
The first output, which is on right at this time, tells us we are ready to start our pulverizer system,
Okay.
which is also status to Forney. Some of our outputs feed hard contact relays, which fire classifier, pulverizer motor, the exhauster motor,
Those are labeled K1 through
K12.
K12. So those are what? Relays?
These are hard contact 10 amp relays. These relays are being interrogated by Forney and also starting the appropriate motors.
Okay. This is electrical drawing 102D9956.
Page 10 of 11.
Page 10 of 11. Alright.
And this drawing covers completely the eddy current clutch drive.
Would you please point to that?
And the cooling system, which is located on the clutch itself.
can we discuss in detail some of the functions of that that are available to us?
Okay, the first thing we have in the upper left-hand corner, button says accelerate.
What should that be set at?
Okay, right now we have it set for 80%.
Okay. Next.
What this pod does, it gives us a ramping feature once we've given it a 420 milliamp signal of how fast that we want this drive to start under load.
All right.
Okay. Next pod on the top right is our dampening. This helps to dampen out any fluctuations in current signal coming to the drive.
What's it set at?
This is set at 100%.
Okay. Next one.
And the next one is our tension sensitivity, which on this drive we're not using. We have it set at 0.
Okay, that's set at 0. Next one.
Okay, the next pot is our max speed for manual.
Okay, I can't see your. Okay. What's that set at?
We are set at 80%.
80%. Okay.
You want to change the maximum speed of the drive in manual. This would be the pot you'd have to change.
Okay, does not that pot actually override in automatic also?
On this drive, no, it does not.
It does not. Okay, so it's only manual.
Only manual.
Okay, what's the next one?
Okay, the center pot on the bottom is our minimum speed for manual.
Or manual setting. That's set at
Manual
what
setting.
right now?
That is set at 0 speed, so at minimum speed you would not be rotating.
Okay, it could actually come down to 0, but you could prevent it from coming to 0 by changing that set point.
Correct.
In a manual mode, or is that automatic also?
That is only in manual.
Only in manual. All right. Next one.
Okay. Next one would be our jog. We can jog any current clutch 0 to 40% of speed of the motor.
What's it now set at?
We are set at 100%, so we can jog the pulverizer at 40% speed.
We also have a torque limit.
Torque limit, yes.
All right.
Which limits the maximum amount of current the pulverizer would handle. It would cause a slipping in the clutch.
Okay. And after we get going, we can set that so in case there's a jam up inside the mill,
Right.
the torque limiter will allow the mill to slip.
Correct.
Okay.
Okay.
Next.
And then on the board next to it, we have our automatic minimum speed setting. This sets our minimum speed for our current follower circuit on the drive.
What's it currently set at?
This is set at 0 speed.
So you can come all the way down to 0 if you want to.
Correct.
In automatic.
Automatic.
Okay, the next one.
Next one is our automatic maximum speed.
Okay, so that can be set for any value that we want to limit the upper range of the mill in automatic.
Correct.
So that a 20 milliamp signal from the boiler will represent the maximum output that Foster Wheeler wishes for that particular set of burners.
Correct.
Okay, that will be adjusted.
Correct.
All right, the next one.
Our bottom pot is a 0 bias pot. This helps to stabilize the interaction between the two automatic speed pots.
And what's it set at right now?
It is set at 6.10.
6.10. All right, anything else in there?
No.
Here we have a Westinghouse 200 horsepower, 1800 RPM motor.
Okay, good Okay, this is drawing 102D 9956, sheet 11 of 11. Alright?
This drawing covers in its entirety the spinner classifier drive. Drawing covers the spinner classifier drive in its entirety, which is a DC drive.
Alright. Show me that.
Drive is located right here.
Okay.
On this small subpanel.
Alright.
Adjust this drive. We have a cell pod, which
What would that do?
okay, that limits the speed time when you give a current signal to the drive on how fast you want the drive to move.
Alright.
Okay, next. The cell, A cell is a D cell. It's how fast you want the drive to stop.
Okay.
Okay, over here, we set our jock.
Okay, which we don't use.
They're not used.
Alright.
We have a minimum speed pod.
Okay. Which we won't use.
We would never use.
Alright, anything else?
Then have our maximum speed pod, how fast we would want the drive to rotate.
Alright. That's set maximums.
That is set maximum.
Okay. Now. That's what now?
Stability is similar to your minimum speed in automatic. Response is your maximum speed in automatic.
Okay.
We also have a current limit adjustment.
Okay.
It's going to limit the amount of current that the drive will pull as it's starting up.
Right now that's set maximum.
That is set maximum.
Okay.
It's a crossover frequency adjustment. You adjust the frequency of the drive firing the SCRs.
I noticed that that's been marked.
Yes, it has.
Okay.
This is a factory adjustment. It should never be touched unless the drive needs to be replaced for some reason.
Okay.
We then have an IR compensation, which is sealed by the factory. It's the
Okay, it's
preset
not to
factory.
be fooled with.
Not to be fooled with.
Okay.
If you ever have problems with the drive, you will get a run lockout light.
I see. That comes on if there's a problem.
Correct.
Okay.
If you get this light, you need to reset the drive. There's a small reset button
Okay.
you have to press. This drawing covers all the pulverizer speed meter, spinner speed meter, pulverizer current meter, spinner current meter. And we have our signal conditioners taking 0 to 40 volt signal, converted to 4 to 20 milliamp signal for the computer to read. Each of the 4 signals.
Okay, you want to show me those units? All right, point them out to me, please.
Pulverizer speed meter. Pulverizer amps.
Now that is in percent. That is not the actual speed.
Correct.
Directly below it are the pulverizer amps. That also is in percent. Is that correct?
Correct.
All right, what else?
Manual speed pipe.
In case you want to go into manual, how do you do it?
You have to put the panel physically in a manual mode.
Show me that.
supervisors have the key.
Only the supervisors have the key. All right. You have to go in the manual. Then through these direct pots, you can set the various functions of the machinery.
Correct.
All right.
And we have our spinner speed, which is 0 to 100%.
All right. That's the spinner at percent and the spinner amp, same as the mill.
Correct.
Okay.
We also have a spinner manual speed pot.
All right.
Our differential pressure gauge.
Okay, let's talk about that. This is not in percent. This is actual inches of static pressure across the machine, or across the pulverizer.
Correct. We have two set points. The lower set point being low QP.
What does that do?
That gives an indication of 40 that the mill is empty. And the upper set point is at the hard limit feed rate into the mill. For some reason the computer starts overfeeding, we can cut the signal through the meter.
Okay, so the upper one is an override on the computer and will actually shut off the feeder should something go awry. What's the bottom one?
Bottom one is our lower hard contact limit telling 40 that we are empty.
Okay, built into the computer circuit is the ability for the computer to tell Barney that we are 1 inch below our ideal set point. This is another hard contact that we can manually set that will tell Barney the same thing. And during shutdown, they will have notification that we have run out of coal, we've ground the coal out of the system, and the system can shut down. All right, what's the meter below?
Meter below is air CFM in the system.
It's percent air that is flowing through the system. This is a Foster Wheeler feedback, and is only displayed on our board.
We also have a control on-off, power on-off. There's a key switch. Once it's turned off, the only reason it should ever be turned off is if somebody is working on the system.
Okay, so you've got an on-off power control for this cabinet.
Right.
Okay, you got anything in the cabinet you want to show us?
Okay. These are all our signal conditioning modules.
Signal conditioning. All right.
Condition the signals from the meters into the computer.
These are the signals that go to the computer?
Correct.
What's that? What are you holding your finger on?
This power supply feeds the current signal through the Delta P transmitter.
Power supply for the Delta B transmitter.
That's all that's in this cabinet.
All right.
This is the lower pressure side. Up over is the pressure transmitter, which then sends a 4 to 20 milliamp signal to the computer. The computer, based upon mill speed, computes a differential pressure that we should be operating, and then in turn generates a signal to the Merrick feeder.
Mike?
This is a Trayvon automatic dribble lubrication system.
Okay.
Here we have under normal cycle, we'll have a green light. When the lube makes a cycle and turns on, we will get an amber light. If at any reason that the lubrication would not lubricate, we would then get a red fault light.
Okay, open the cabinet door.
Inside of the panel here, we have two means of operating the loop cycle. One, we can press this button here for a manual loop,
All right, what you did?
will operate the barrel pump. When we press the button, we went from a green light initiation by the cycle timer.
All right.
This different solenoid to the Trayvon barrel pump, which
All right.
is
Now lubricant out of this barrel.
out of this barrel. We're
Now,
using
what's in that barrel?
This has a lubricant Mobile Temp 78.
That's a high temperature lithium-based grease. All right. Now that pumps the grease from there where?
It comes out through this fitting
Okay.
to there's a high pressure indicator which we're operating at about 1,000 to 1,500 pounds per square
right.
inch. If we get an overpressure in the line, a blockage, rather than rupture a line downstream, we have a rupture disc here that is set to relieve the pressure at about 2,000 psi.
Okay, where's the grease then go?
The grease that comes on through this filter, goes out through the line to this distribution block.
To a distribution block, all
Yes, sir.
right?
Here is a cycle switch. Whenever the lube unit goes through a cycle, it has to go through a cycle and make this switch to know that we have completed our lubrication cycle.
All right.
It comes down through the block and splits, and we have one line that goes on. This line goes on through a broken line indicator.
What happens there if you've got a broken line?
We get an indication, we get a drop in pressure, and we have an actuation of this switch, knowing that we do not have pressure, back pressure on this line, and it gives us a fault indication. This line goes off to the inside of the pulverizer to lubricate the journals and the top mill bearing.
All right, you got another one?
This line here goes off and goes to the bottom of the pulverizer and lubricates the bottom mill bearing.
Ask Mike to activate the lubrication cycle so we can see what happens. Okay, Mike. All right, again. Push the button.
handheld terminal. Okay. And I'm going to zoom down on that. And would you explain a little something about the terminal for us?
This is the handheld terminal for entering the parameters which operate the mill. The terminal has an LED display.
Okay, hold on right there. I'm going to turn off the lights so maybe we can see the LED display. And would you hold it up straight at me now? Okay.
This is the normal display.
Cock it just a little bit, I'm getting a light flare. There it is. What does that say? It says,
Williams DF mill.
there it is. Williams DF mill. All right.
After powering up the computer or resetting the computer, this is the display you will see. You may also notice that after about 3 seconds it blinks. This is part of the self-check of the computer when it turns on.
Could you show me that? All right.
The keyboard has a numeric keypad, numbers 0 and 1 through 9.
Okay.
Several of the keys we don't use, but the very important ones, first of all, the mode of operation. To set up the parameters of the mill, we push setup.
Okay, let's start about what are these setup parameters. There's a double EEPROM that allows you to set variables inside the computer. Is that correct?
That is correct.
Okay, so now we're going to take a look at the first variable. Is that correct?
That's right.
All right.
The first variable in the setup, variable number 1, is the minimum operating mill speed.
All right.
And you can see that it's set for 60% of scale. And that can be changed by pushing the increase button or lowered by pushing the decrease button. And whatever number you want to leave it at, for instance 53%, you then push the store button.
All right.
Until you push store, you haven't really changed the number that the computer is using. When you push store, the store light comes on, and at that point the computer has entered the information into the double EEPROM, the non-volatile memory, and it will remember that even when the power has been turned off.
All right. Prove to me that you've actually gotten it in there. Go to another number.
If we go to variable 9 and then back to 1, we have 53% in there now.
Correct. Would you please set it back properly now?
All right.
The proper setting will be 72%, as will be shown later. Okay.
We're back to where we are. If we just want to scan the parameters that have been set up, we can repeatedly push the setup button and scan through the various parameters. Or we can even hold that button down and it'll automatically step through to get to some of the upper parameters.
Okay. Hold that a little more. Go ahead.
The next mode is the monitor mode, and that aids us in checking out problems in the mill control. We push monitor, and similar to the setup mode, we get a channel number, which is an address in the random access memory of the computer. And if the computer is operating, we can actually watch something change. For example, the ideal delta pressure of the mill or the meter speed command by holding down the monitor, and each time through the computer's operating loop, which is about twice a second, it will update this display and we can watch parameters change. But that's strictly used in checking out internals of the computer capability.
All right. For right now, would you please cause the computer to fail by removing one of the boards?
All right, what I'm going to do is turn off the power of the computer.
All right.
And I'm going to pull the analog to digital converter board.
All right.
I don't even have to get him out the cage, but just loose from the back point.
Okay, it's now loose. All right.
Notice that we've had a failure of the built-in test. The light above the B button should come on, and the mill will not operate.
Turn it on, please. Now, you can see that we've got the bit failure light.
We should should also point out that we did not get pulverizer ready to start.
Now, you cannot go forward any further, is that correct?
That is correct. We have to go to the handheld terminal and see what failed
All right, would
the
you do
built-in
that?
test, and that is done at location 99.
99.
We have to go to the setup mode. We go to 99, and we see that it's a
All right.
102.
Show it directly at me, please. That says that you got a failure at 102. Is that correct?
And we look up in the documentation and find out that it's a failure of the analog to digital converter.
Okay. Having found that and reset the board,
Reset the board. Turn the power off first. And we fixed the problem, but even fixing the problem, when we can turn the
okay,
computer back
turn the
on,
power on.
we're still going to get the failure.
We've still got the failure up there.
We
All
have
right.
to acknowledge to the computer that we have fixed the problem. That will aid in finding intermittence and things of that sort.
Okay.
So we're going to go to the setup mode, to channel 99, and to
Alright.
clear that number, we could
Directly at me so I can see it.
decrease it, but that takes a while, so we hit the B button.
Hit the B button to clear it. That sets it back to 0.
Now we have to store
Now
that.
you have to store it. All right.
And sure enough,
Now the system will start back up.
and we are now indicating pulverizer ready to start.
Okay. Now that's the only way that you can get the pulverizer to start again. You must acknowledge the fact that you had a bit failure in the computer, reset it to 0, and store that value.
That is correct.
Are there any other failures like that?
Yes, sir.
All right.
Read those off the list to you.
So why don't you hold up the list? Built into the program.
Built into the program, when it comes on at power up, it checks the watchdog timer.
Show me some of those.
The watchdog timer is located on the signal conditioning board.
What does the watchdog timer do?
The watchdog timer protects us in case of a computer not failing hard, but going kind of crazy. And if the computer does not, every time through its loop, say, "Hi, watchdog timer," in about 3 seconds, he will time out
And
and
this keeps
reset the
the
computer.
computer from going off into space.
That's correct.
All right.
Besides the watchdog timer, we check the random access memory by writing a pattern out there and reading it back.
So in effect, the computer checks itself. If it fails, it's going to notify you how it failed, and you cannot proceed without first clearing the failure.
That is
And
correct.
to do that, you have to dial it up there under the setup mode, and having done that, clear it by hitting the B button, and then store that information.
That's correct.
That was the only way that you can proceed. So if this machine ever locks up on you, make sure you come over and look for that bit failure light that's on.
That's correct.
And if it is, the only way out of it is to acknowledge that failure and reset to 0. Okay, one other thing, is there a timer on this would tell you how many hours you've been operational?
Yes, sir. That's at location 100.
100. Would you show us that? Okay, and right now that shows
0 hours.
0 hours of operation. This would basically tell you how long the machine has been operational. Every hour, the computer writes to the memory bank, the EEPROM, and updates on the hour, or any combination of shutdowns, it will write directly. Any failure, it will write directly.
That is correct. Been tripped out by an external trip, and that's normally the Forney flame safety system dropping OK to start or dropping permission to run once we've been running. And we display on the handheld terminal
All right, pull that over here.
that we've had an external trip.
In other words, you're telling me if, for any reason, we drop off, not due to Williams control, you will notify that there's been an external trip.
That's correct. And that stays until the next trip. So
Okay.
even if we come back up and run, this will stay in the display unless you hit another button of any kind.
Okay, now let's suppose that it's not an external trip and it's a Williams trip. How can you determine what stopped you?
Well, if it's been a Williams trip, you'll get the Williams DF mill display again.
Okay, give me that. All right, that's the Williams DF mill display.
That's correct.
The unit has tripped. Now how does one go about finding out exactly what tripped it off of the Williams panel? We recognize the fact that Farney will be showing us what tripped, but how could you also see it at the Williams panel?
Well, here at the Williams panel, you go over to the output devices, the black solid-state relays,
The ones that we looked at before, right?
and they're labeled, and they say things such as spinner start failure, exhauster motor failure.
We have begun a startup, and in 30 seconds, we're going to have a failure. What will it be?
Should be an exhaust fan failure.
Point to it.
Right there. And if you look real quickly, that LED actually came on about a half a second before the indication of shutdown started and shutdown complete.
Okay, so now that we can walk in here and we can look for the LED that's lighted for a failure of the Williams panel, would you please explain, if we go into the setup mode, would you please push that button? You see the setup light comes on. And now, in that mode, would you begin to, I see item number 2. Somehow we got up to that. Would you go back to 1?
That's the previously entered item
Okay,
number.
let's go to 1 and
Enter.
enter. Now, you see that set for 72. Would you please explain what that is? You have a sheet somewhere that
Yes,
would
sir.
explain this?
We
Let's
have
see.
to sort of do a balancing act, but this is the setup sheet, and we keep this on file in the computer.
Okay, and those values show on there. And item terminal address, number 1, it says maximum operating mill speed.
This
And
is,
item 2, maximum operating mill, minimum was first, maximum second.
That's
All right, let's take a look at the handheld now. And so that shows you the value that we set in there, and that's the value that we want to keep in there all times. The 72% represents the starting position for your roller mill. That's the minimum position.
not necessarily the minimum that the roller mill will operate, but the minimum point that we use to reference some of the other parameters we're going to set.
And would you step through that and read off?
Now I can step through that merely by pushing setup, and now I'm at number 2, and that, as we indicated, is the maximum operating mill speed, 99%.
Okay. And let's stop. We have the terminal in front of us. Items 2 is set at 99.
That's right.
Now items 3 is the spinner speed percent at
Whoops.
minimum mill speed.
We got ahead of ourselves.
We've done 1 and 2.
There's 3.
3 is at 30. 3, the spinner speed is used to increase or decrease the fineness of the product being burned. Higher percentage gives you finer. So we have set this at 30 and have determined at that setting we get 91 to 92% minus 90 mesh, 200 mesh. The normal is 70 minus 200. So any finer is kind of ridiculous. Would you go ahead? Now, would you show the complement? Okay, 4 is 46, and 4 up here says that the delta pressure ideal at minimum speed. All right? That means we have a target of 46% of a 15-inch scale, which is, I believe,
About 7.8 inches.
7.8 inches. In other words, this reads as a percent of the scale. And the
That's
scale
correct.
is a 0 to 15-inch scale, so you would take 46% of 15. And that would be the set point. All right, would you go to the next one?
We're not using number 5 anymore, so we leave him at 0.
5 is not used. 6, spinner speed.
percent maximum decrease. And how's that used, Jim?
That sets the rate limit to drop the spinner speed. We allow the spinner speed to drop as much as 5% per second.
Okay, 5% per second. Go ahead. That's something would never be changed.
That's correct.
7.
The spinner speed minimum command, and this again is a percentage of scale, and we have him set to 0 to allow the spinner to be commanded as low as 0
speed. Okay. Later on, if somebody was worried about the spinner shutting down, they could increase that to approximately 5% now because we're running at a higher spinner speed.
That's right.
All right, the next one.
Number 8 is the feeder speed maximum decrease. This is just like for the spinner, except now that we have our new control algorithm, this tells us the range that we will allow the feeder speed to drop from the calculated target, which is based on boiler demand.
All right.
We have him set to minus 10%.
And again, this wouldn't be changed.
Never. Number 9 is the feeder speed minimum command. Again, we can command a minimum to the feeder of 0.
And what do you have in there?
It is 0.
Okay. Step again.
Number 10 is the maximum allowable milliamps at minimum mill speed. This parameter allows us to set the computer for the wear alarm so that we can detect journal or bearing wear problems.
Okay, this has not at this time been set because we do not believe that the mill has been run in properly to determine how that should be set as yet. That will be set later on.
Number 11, and now we're into the complement pair, Bob, of the above parameters.
In other words, we are looking at the opposite of number 3.
That's correct.
3 is the spinner speed at minimum. Now we're going to look at 11, spinner speed at maximum mill. All right, what is that set at?
That's 25%.
Okay, now you notice before, number 3, minimum was set for 30, and maximum is set for 25. What that means is as the mill speed goes up, the spinner speed goes down, maintaining constant 91, 92% minus material. Okay, next one.
Number 12 is the ideal delta pressure at maximum mill speed. It's set to 67%, which is just a fraction over 2/3 of scale, or 10 inches.
10 inches. Okay, that has been set and should not change.
Number 13 is the feeder conversion factor. This is the factor that we calculated boiler demand, and then we multiply the boiler demand by the linearizing factor of 85%, and that goes out as our feeder command.
Okay, that's set at,
85.
all right, 14.
14 is the spinner speed maximum increase. Up above on number 6, we had the spinner speed maximum decrease. We now have the maximum increase. This is how much we allow the spinner to speed up per second.
Okay, that should not be changed, 5%.
Number 15 is the spinner speed maximum command, and we've allowed for the full range of spinner up to 99%.
All right.
Number 16 is the feeder speed maximum increase. This is the amount of topside feeder speed correction that we allow from the target. It's set to 10%. Number 17 is the feeder speed maximum command. It's set to 99%. Number 18 is the maximum allowable milliamps at maximum mill speed. We haven't set that, as you noted above, and so that's still set at 99%.
Okay.
Number 19, now at this point we're out of the pairs of values. Number 19 is the spinner speed minimum alarm value. We currently have him set to 0, and and we'll probably come up with a setting probably of about 5%. This is the alarm value. The computer looks at the spinner tack, and if it ever sees the spinner tack go below this value, it shuts the mill down.
All right.
Number 20 is the mill speed minimum alarm value. Exactly like the spinner, except it's looking at the pulverizer motor tachometer. It's also currently set to 0, but we'll probably leave it with a setting of 5 or 10%.
Why don't you do that at this time
All right.
so that we can look at it? We
To
are
make
going
this
to hit.
5%, I'm going to push the increase button.
All
And
right.
I can just hold it in, or I can step it individually.
All right. Having gotten it set.
Then I have to push store.
The light came on.
That says that the
Yep.
computer has accepted the value.
Okay, so now the mill, is there a timer that lets the mill get up before that's looked at?
Yes, there is, because there's a 5-second delay after we engage the ECC during startup.
All right.
Number 21 is the panel alarm timeout value in seconds. This is the time, if you push the DP alarm reset on the local panel out by the pulverizer, that you have to clear up a problem before the alarm will repeat.
All right.
22 is the exhaust fan startup delay set to 30 seconds.
This could be reduced if you want to, because apparently your fans are across the line, and it could start in maybe as little as 5 seconds. Allows the program to continue. All right.
23 is the low delta pressure timeout in minutes. This is the time that we will allow the pulverizer to run below, at a certain level below target delta pressure before we signal the 40 flame safety computer with an alarm.
Correct. Now, there is going to be another factor which indicates that we will not begin counting this time until we're certain delta pressure below our target. And what number is that?
That's number 26. It's called the low delta pressure startup time.
Let's go look at that and then we'll come back.
26.
26 says
30 minutes.
we've got 30 minutes and nothing's going to happen for 30 minutes until unless somebody does something about the delta pressure being too low. Now, that would be an indication if the feeder runs out of material. And that happened today. The material was stuck in the feed chute, clay packed in there, and the low delta pressure shut them down after they ran out of material. Okay, go back to
24. 24 is the milliamps too high alarm timeout. We had the setting for the milliamps up above. This is the time that we will allow the milliamps to be above that line before we declare the wear alarm. In either case, we're talking about a non-fatal alarm. It's a warning.
So you've got 10 minutes,
Yes.
and this is a deep balance type thing. It has to be really proven that it's over. All right.
25 is the air seal pressure alarm timeout.
All right.
We allow the air seal pressure to be low for this amount of time, giving a warning alarm before we declare a fatal alarm.
26.
26 we already did, that's the low delta
Right.
pressure startup time.
And 27.
And 27 is the low delta pressure calculated limit. Besides having a low delta pressure switch on the delta pressure meter of the local panel, the computer calculates how far delta pressure is running below target delta pressure. And this is the value of that it would allow below target.
And
At
what
the-
is that? It shows 0.
Shows 80%. I'm going to change that to 20% because that's where it belongs. I'm holding the decrease button in and it automatically steps down. And when I get to 20, I push store, and that's now locked in the computer.
And it should be 20, not 80.
That's correct.
Okay. All right, now, we're down to 27. What's that?
Well, we just finished 27.
Okay, 28.
We don't have anything at 28, and that's signified by the -1. 29, 30, 31, and 32. Those are all empty. They're not
I
being
see.
currently used.
33, 4, 5, 6, 7, and 8. What are those?
33 is 0.
Okay, these are digital filtering constants, and they really aren't anything that you should worry about, except we're going to tell you what they are. 33 is 0, 34 is 10, 35 is 0, 36 is what?
1.
1, 37 is
99.
99, and
38,
38,
25.
25. Those are constants that should not be fooled with. Anything else?
That's all.
Daily arrivals of coal trucks dump their loads at the scale and stockpiling area. The 2-inch by 0 coal unloads through a grizzly and is conveyorized to stockpile as shown to the upper right, or continues on up the primary crusher house in the center building. Output from the primary continues up these conveyor galleries. There are dual conveyors that bring both coal and shredded bark and wood to the boiler. Bark is in the conveyors to the left and coal to the right. By removal of the hinged door on the Merrick feeder, we can see inside. Never do this when the pulverizer is operating.
Come down this belt, and drop down this chute. There's a plug-up, there's a rotary switch there, which will indicate that material is plugged this chute.
Now with the door replaced and bolted tight, the mill is brought up to 92% load, and we can now see the raw coal feed through the viewport. The coal contains 7% moisture and has 13,000 BTUs per pound. The raw coal drops down the stainless steel feed pipe into the pulverizer. Control of the coal feed rate is by the Williams microcomputer, which sets the feeder rate to exactly match the boiler demand signal.
Coming down and into the mill. You cannot hear the mill in operation.
Each Williams DF mill is equipped with a tramp metal throwout. By opening this large gate, removal of tramp metal and hard-to-grind materials is accomplished. This is normally done periodically. Hard-to-grind particles such as iron pyrites, slate, and gravel will accumulate at the bottom of the fluid bed and can be dropped out of the system as needed. In addition, should it be necessary to empty the feed chute or mill for any reason, opening the gate and jogging the mill will do the job. The Williams patented DF pulverizer is manufactured in capacities ranging from 1 to 23 tons per hour of coal. The mill's drive skid assembly, shown here, is skid mounted for ease of removal.
200 horsepower motor. Rolling motor.
The pulverizer cross-section, shown here, has a large access door through which journal assemblies are easily removed for yearly maintenance. So that we can better understand the overall mechanical function of the DF mill and their lubrication requirements, we show here a shop view of 6 mills under construction at our plant. The mill to the left has its cover and journals removed, while the mill to the right is complete with spinner separator. The mill lubrication system has several checks, the first of which is the broken line indicator.
And what you are pointing to is what is known as the broken line indicator. Is that correct? All right. And point to the switch to your right, which is what we are using to indicate that a cycle is complete. For purposes of this movie, we're going to deliberately go in and break one of the lines. Okay, so now we're breaking. That's it, hold it right where you got it. Yeah. Broken line. And as that grease comes out, would somebody point at the broken line indicator? All right, that indicator has now gone in. All right, indicate now the grease goes down the hole. Grease goes down into the hole, out into the block, through that line.
All lubrication points inside the pulverizer are lubricated from one common distribution block. All lines are high-pressure steel hose, covered with green abrasion-resistant sleeves. The journals are free to roll over uncrushables and pivot back out of the way. There are no springs or spring controls.
No, the journal itself. Rub it against the bull ring? Yeah. Unscrew the oil check plug. All right. And with the dipstick, would you please check the oil level? All right. And that dipstick is kept on the inside of the cover. And there's a notch on the dipstick. Is that what you're showing me? Yes. Right. And that shows the level the oil should be at.
Capacity adjustment is achieved from 100% to 0% output by varying the central rotational speed. Since centrifugal force varies as the square of the rotational speed, so production will increase or decrease accordingly. Air is used to dry and convey the pulverized coal. Shown to the left is the hot air damper. Central is the positive air shutoff damper used to isolate the system from the boiler. This is called the Paso valve. And to the right is the fresh air tempering damper used to control the mill outlet temperature to 150 degrees Fahrenheit. The hot gases are conveyed to circular bustles, which we call wind boxes. These wind boxes surround each pulverizer, and they introduce air equally around the periphery so as to fluidize the coal and dry it, and convey it up to the active classifier we call a spinner separator. Because of the active classifier design, sieve analysis for the pulverized coal remains constantly at 90-200 mesh. At high or low loads, there is 0-50 mesh oversize. Pulverized coal and air rise into the separator, where spinning blades force the heavier particles back down for regrinding at the mill zone. From the splitter valve, 2 pipe runs are used to transport the pulverized coal to each burner. Each pipe run has a coal flow cutoff valve, which is driven by an air cylinder. These valves are always closed when the pulverizer is shut down. This Foster Wheeler burner is equipped for coal, number 6 oil, and gas fuels, reducing the turbulence in the inner annular region nearest the fuel while directing the major portion of the air to the outer annulus, lowers the flame temperature and NOx.
The back wall of the burner where the burners are located. Okay. This is the front wall of the boiler. Notice the absolute lack of sparklers. Minus the coal is 91% minus 200 mets, and there's 0.8% left in there. Front wall of the furnace at the upper location. Okay, and for these purposes, I will put a blue filter over the camera. We'll now look in at the flame. Running without igniter, so this is a total coal flame.
just got that one like that. See what you see.
Probably should get it on a little different angle. See, maybe we can sort of move it, trying to get it so it's on a better angle so we can see the pin. Sort of turn that one roller a little bit. Really see the pits in it. Where's the one with the real groove in it? I think that one's it. You can really see a groove there. And you've got about 8 rollers there that have got some degree of pitting on them. There's another one.
They're on the bottom, the top. There's 2 of them here on the bottom. Another one there on the bottom. Another one here on the bottom. This one all the way around. This one's got some pitting in it.
Yeah. That's
There's
it's only
back
on the
top.
upper race of the upper bearing. You can see that. Okay. This shows some wear where the lower portion of the upper bearing had spun or worn against the shaft of the journal. You can see where it's been indented. There's a corresponding shiny spot on the shaft. Yeah, I guess that's good. Now the race on the left is the top of the top bearing race, and the race on the right is the bottom of the top bearing. your left. Okay. I'm looking comfortable. All right. Okay. Now we want to bring those up real close, and I'll put it into macro. You'll see the difference in the inside of the racers. Bring the top one in first. You can see we have a real mirror finish, slight amount of pitting. It's an amazingly hard surface, very shiny. Okay, bring the bottom brace in. Bottom brace is not nearly so shiny. It's more of a satin finish. A little bit of a difference. Top bearing from journal number 11 reassembled, and you can see the play, which is even more than the bottom bearing on the same journal. Considerable amount of play. That's good. Okay, these shiny particles that we're seeing now down inside the journal look like pieces of chrome and metal from the bearings themselves. We've got a little bit on a rag right here too. I'll focus in on it for just a second. This is the bottom bearing.
Right, right. Keep it back, keep it back, keep it back. Okay, right in there. All right.
Bottom bearing, or some play. See that?
Yeah, all right. You're picking it all. Keep it a little over, a little bit, no. Okay, right in there. Okay, good. Stay right in there. Bring that forward here a little bit. I guess that's as close in as we can get it, really. Close in as we can get it, I guess. That's good. Keep it going.
Okay. This bearing, the only wear was as far as the movement on the clearance here. You've seen.
Okay. Point to those rings inside there. You know, on the inboard. Looks like those things have been rolled on the inside. They have.
Oh, inside here.
Yeah.
Yeah, it looked like it turned on the
Looks like
shaft.
that's turned on the shaft, doesn't it?
Well,
So
now
they're angular.
there's nothing to hold this bearing from turning.
Yeah.
So this
That's
is
the
split
bottom
shaft.
330 bearing, right?
Right.
Okay. Okay.
Okay, the upper bearing.
Push that one all the way down. Push it up further. Okay, good.
The upper bearing had a lot more play in it.
All right. Point to that mark in the inside there, right underneath your thumb on the, right there. Yeah, good. Turn it around, drop it down a little bit. Okay, that's good. Yeah. You can pretty well see that. Yeah. There's no scars on this bearing. Nothing other than just from the end play wear. See that inside there now? This bearing, it came out of the journal that the first one that we rebuilt for Comco. It's #1 journal. It's got Mobile Temp 78 grease, and apparently has more wear than the original bearings with the SP3.
Move it back a little bit. Move it back. Okay. Stay in the picture. Okay. I can see Mobile Temp 78 on there. All right.
Now there's quite a bit of wear on the outside here.
Yeah, take off that inner ring and you can show that wear. Hold it up there and turn the ring, turn it down. And put your finger on that inside of that ring there where you can see the grooves where it's worn in there. Yeah, no, bring it down a little bit. Bring it down a little bit, Ernie. Okay. Bring it down a little more. And turn it a little more to the side. A little more. Rotate it a little bit. Rotate, no. Twist it to you. Yeah, right, like that. Now we can see the inside of the ring. Point to those two ridges on either side of the inside of that ring.
These ridges
Right,
here.
right there, and then bring it and then one up. All right. That shows you that there's some ridges in there that's been from the wear. Well, that one is fairly well polished, and there's no apparent brunelling in there at all, is there?
No.
Falling. Okay. What we ought to do is now we got the lights on, and bring that other one back over here again, too. That was the bottom and top. You can probably see that one better at the bottom.
Bottom of the bottom bearing.
And then that has been
top.
with Mobile Temp 78, right?
Right.
Those are both out of the same journal.
Shows the square here.
The grooves where it shows it's out, that's the bottom bearing, and it's obviously turned on the shaft. Apparently the friction on the bearing itself is greater than the friction on the shaft. Let's see, those are the ridges in there too, are they not?
Very little.
Very little to
There's
show?
some, but and here.
Okay. Okay, keep it in there. That's good. Bottom. Okay. Is that all we're going to do? Are you going to take the other ring? Are you going to take the both outer rings off and take the spacer ring out?
Good.
There's no spalling. There are all the
No
rollers.
wear.
Are there any chips on any of those rollers?
No, not on this bearing.
Is there any apparent wear on any of those rollers there?
The only wear that I could see is in the race itself. The bearing itself, it seems to be in
Hold it
position.
steady right there. Just a minute. Let's see if I can bring it in. That's tighter than you can get it.
Now when I cleaned these bearings up, they were real stiff, like it had a gum or a rosin or something. I couldn't hardly turn them at all on both bearings, top and bottom. That's grease.
And this is a residue of the, that's not discoloration in the rollers.
No, that's just grease on them.
That's no trouble for you. Yeah. Go on, yeah, okay.
Nothing on
Bring
the
it down just a little bit. Bring it in a little bit. Okay, that's good. know that inner ring there, and you run your thumb around and show how it's been polished up. No, not that's the spacer ring. That inner ring there, that you have that top that's right underneath your right, left hand there, right there. Yeah, take your thumb in there and show how that thing can be. Bring it around a little further, bring it a little more, bring it further in. Okay, yeah. See, that's not a burnish on that. Okay.
No, it's just grease.
That just discoloration from the grease. There's no vernelling or any other signs of spalling or wear in there. It's just that the grooves or the rolls themselves are worn that track in that bearing. In other words, obviously the bearing has worn by that amount. Because those grooves are obviously not in there when that bearing is put together. That's where the bearing wore. Okay.
I'm going to show something different. Out of the
By side there?
how to get them here.
Okay,
Mobile Temp 78. This is the top bearing. You notice that the play that was in there, the amount of travel the bearing will move. Now, the SP3, which is an older bearing, had somewhat less play in it. Didn't have near the wear. Now, this is the one that Dave showed. That's it looked like it had worn quite a bit.
But point out the grooves in there. See if there's any grooves in there at all.
Yeah, there's some
The grooves are
small
more or less
grooves here.
minute compared with the one in the other bearing.
This is the one with the pitted spots in the bearing.
Okay, can you take a screwdriver and point a couple of those?
This bottoms of them here.
All right, let me zoom in there.
Okay, around here we got top and bottom pitted.
Okay.
Here's one with a large groove.
All right.
Two bearings, two of the rollers were in bad shape in the center.
All right.
These are on the bottom, a little bit on the top, and on the bottom.
Anything else you want to show us?
Okay, this is...
Yeah.
You want to read them off for me? MT78-2. Alright. Now let's take a look at that journal. You want to move some of that stuff around for me? Break it in your hand if you can. What does it look like?
Looks like coal. It looks like bait. There's one piece here with the spring in it. I'll
Get the spring out of the seal. Alright.
There's no seals in it. There's gone.
There's no seal in there at all?
No.
Okay, lift that stuff out of the way. That's it. Just take it off.
Probably need to put it in. There's part of a seal coming out there. That's part of the seal.
seal at all, is it? The seal is gone. Get it from this side. So the seal is completely gone. Both seals. This one was, this journal was composed of 2 seals standing up vertically, as I recall. Those seals are gone. Alright, that's close enough. Alright.
Okay. This is all worn out right here.
It's worn out?
Worn.
Yeah, it's worn. It's been depressed. Okay, let's see me zoom in on that. Alright, go ahead. Is there any coloration or discoloration?
It's kind of a blue color like it's been overheated.
Alright.
The seal carrier here has been it's been a pretty hot visit. It's been
Alright. How about the shaft?
shaft discolored, one color here and another color down below.
The upper portion, does it look straw colored?
Right.
Yeah. Would you say that this has been overheated?
I would say it was.
Alright, looks like a temperature problem. Okay, thank you, Bob.
Okay, we have a worn area here
That's worn.
that we've never had before.
Never had that before.
Not like that.
What's different about it?
It's deeper,
It's worn.
worn deeper,
Yeah.
and farther down than I've ever seen it.
Alright, what's up above it? What's in there?
And here the cage,
You got a screwdriver or something to show me what you're talking about?
we have a cage, bearing cage, is just tore all to pieces. There's a piece of
That's the bearing outer cage.
cage
What's around to the left right up in there? Yeah.
here.
Right, I can't
That's
see
full.
that. Push that around so I can see it, please. Pull it right down there where it was. Okay, can we turn the journal around?
They're not much weight. The bearing cage
This is the bearing cage itself.
is just tore all to pieces.
That's the way it was as it came out. Is that correct?
That's the way it was. The rollers are all down in there, all
All right. All right. This is MT5. This is the next one that came in. And go ahead and pry that seal out for me, please.
this is just a part of the seal.
One of the seals, it had grease in there.
It had grease all out here where it had come out. Got plenty of grease on it.
All right.
The shaft turned. Not locked up.
Okay.
So far, that's about all I found. Now we put
Where's the cap for that?
it's right
For
here,
number 5.
number 5.
MT78-5. All right. Will you point to the air seal? Is it plugged?
Good. No, it's not plugged.
It is not plugged.
Not plugged.
How can you tell?
Well, when I took the air seal off, it wasn't even plugged. It was clean.
All right. It was clean. And you can see where. Have you moved your finger in the air? Is that
No,
where the air was
no,
coming
that
in?
is where the air was coming in, right
All right,
there.
so that's a sign that the air was actually going in there at that location. Okay. Number 2, and that's the way it came off.
The
It's
way it
clean.
came off.
Is the air seal blocked?
It's plugged
Show me.
right here.
Tip it down. All right, it is plugged.
Filled with
And that's number 2.
number 2.
This is MT78, and this is the way that it arrived. shape are the seals in? And is there any grease in there? Okay, pick that up and show me the seal carrier, please. Hold it right about at that level. Yeah. It's a seal carrier.
Pretty good shape.
And are we looking at, turn it kind of sideways, so that's it, like that, hold it right there.
Don't appear from the odor and appearance it might be contaminated with SP3.
Does it smell like SP3?
Yeah.
It does.
Yeah.
I think maybe there's a chance that they have been using the wrong grease in this.
I would think so.
How are the seals that are in the front there?
Well, they're not. They're not in too bad a shape.
Was this journal movable when you received it?
Right.
Okay, put that down. Rotate the journal for me. Can you twist that by hand?
The O-ring also is in good shape on the seal carrier.
All right, can you rotate the journal by hand?
Rotates very easily.
So there's some question as to why this journal was sent back.
Right.
This is a close-up of the seal area there. All right.
The lubricant.
Top to the unit, would you please point to the grease that's in there? And it looks like taffy. Can you move some of that around? Would you say that's contaminated with coal?
I would say so, yeah.
Yeah. Can you find the air seal? Oops, don't touch it. I want to see it. I want to see it. All right, tip that thing towards me if you would.
There's the air seal right there.
Is that thing plugged?
It's got grease in it. It's not solid, but it's partially filled with viscous type grease. Not hard.
Okay, but it is plugged.
Right.
All right, thank you. This number 12 journal, this is the last of the journals. Would you please show me that grease? Is it rubberish or what is it? That's the SP3 grease?
Right.
Okay. So this is the last of the journals that had SP3 and has been in operation now for about 8 to 9 months. Will the shaft rotate? Right. Okay, let's see if the shaft will rotate. Okay, will not rotate. For seal now, is there anything in there?
That's seal missing right there.
Pieces of the seal are missing. All right.
here, it's good.
Okay, it's gone. It's shot, right? Okay, thank you. That's the that's the. You can go ahead and pull it out. Okay, hold it up so I can see it. Yeah. Kind of poke around in it if you would. Okay, all right. After number 12 journal, and would you show me whether or not the air seal hole is plugged? Can you dip that cap up so I can see it? That's it. All right. Yeah, so it is plugged.
Right.
And that cap has not been cleaned. That's the way it came off.
Right.
Perfectly clean except for that. Now, hold up the air seal unit itself, okay? Yeah, we'll put that down next to that. And that shows the coal up inside that air seal unit. All right. Plugged in both directions.